Basically, I'm going to cut it anyway. Anyways, all right, guys. Yeah, welcome to the second lecture. Now, let me give you a brief introduction what we are going to do. It's going to be technical. Most of the things are just basically there for you to understand what stochastic processes are going to be like. Okay, I'm going to come back to those issues, but these are the ones that I'm going to discuss. So again, I wanted to give you a little or proper definition of random variables, and including measures as well, and in particular the probability measures. So you're going to see basically some properties on that, okay, among others, sigma additivity and so on. I'm going to look into especially the properties that are true, let's say, almost everywhere for a function most of the time, okay? So I want you to basically basically consider that one, and also including, in case of probabilities, almost sure events. That's not the same thing as basically the sample space, if you would consider the sample space to be an event. Anyway, which it is. Now, we're going to look at so-called measurable functions and random variables as well. Random variables are measurable functions. A function is going to be measurable if basically certain properties are true, and I'm going to discuss them. And in particular, based on that, I will also create the cumulative distribution function and discuss basically the issues with that. And we're going to look at limits and continuity and all that stuff. And next time I'm going to address asymptotics based on probabilities, so that's going to be important as well. And in particular, I'm going to look at continuous functions, uniform continuity, absolute continuity, and stuff like that. So these are going to be issues that I'm going to discuss today, okay? Things are, I mean, not everything is going to be important, so I will basically just consider those quickly, okay? But maybe you heard the term Càdlàg function, so that's going to be one. And limits of functions are also going to be an issue. However, continuity is also an issue, especially for cumulative distribution functions. But I'm going to define also, I'm going to a little bit go further to see basically other issues as well. So you see basically what those things are. And in particular, I'm going to define continuous random variables properly. Now, maybe you remember basically what we were looking at. So in particular, when we look at some measure, okay, so we're going to look at some function that is based on the sigma algebra. Okay, so we have basically a sigma algebra on a sample space. A sigma algebra is a family, as you remember, which is closed under, number one, complementation, and closed under countable unions, number two. And that basically were discussed then in detail. And a family is, of course, a subset of a power set of mostly, I'm going to refer to the sample space as well. So that is basically what the, let's say, the domain of the function is going to be. And you have real numbers coming out, okay? And you have different properties that these functions can have, among others, additivity. Now, a function is called, based on that, so-called pairwisely additive, that's the term, if actually the image of a union, so let's say you have pairwisely joined sets, and pairwisely disjoint sets are, let's say, A and B. What does that mean? I mean, there are disjoints, so the intersection of the two is empty. Okay, so that's basically the issue. So pairwisely disjoints means that the intersection of the two is going to be empty. That's it. Now, if the intersection of the two is going to be empty, the image, okay, so anything that you put into a function, and the function is called lambda here, the image of a function, or the image of a union, okay, sorry, the image of a union of the two is going to be the sum of the images, okay? So that's going to be the image of A plus the image of B, if you consider basically the image of the union of A or B, let's say, okay? So that is basically the issue here. This is called additivity, by the way, and I'm going to refer to as pairwisely because you are only considered two, okay, in this case. Now, if you consider more, but let's say the number of sets that you have is finite, so then you will consider it to be the property which is finite additivity, and finite additivity is going to be equivalent to pairwise additivity. So those two are going to be equivalent. What does that mean? This means the following. So when you consider basically a union of those sets which are pairwisely joined respectively. Now, what does that mean? This means if you pick two, let's say you pick AI and then you pick AJ, and then you basically take the intersection of the two, you'll find that this is going to be empty, but only, of course, if the indices are different, because if the indices are the same, you know, any set where you would consider that to be the intersection with itself is going to be the set itself, right? So the operator intersection is going to be idempotent in that case. So, but you will only consider the sets which are different. Now, if you took basically take two different sets and then you find that the intersections are empty across all the board, okay, then you will have basically pairwise disjoint sets anyway. All right, now this is going to be the same issue. So if you have the image of a union, so that's the union of the sets which are pairwise disjoint, and you put that into the function, because the union is of course also an element of the family. Keep that in mind, because the union is closed under, the family is closed under pairwise / finite, and then in this case also countable unions. So that is also an element which must be basically declared, and that is defined for every element of the family. Now this is going to be the case. I don't know, maybe I'm too loud. I'm not sure. Apologize. So the image of the union is going to be the sum of the images as well. Okay, so that is still true even if you have more. These two are equivalent, by the way. Okay, and that is the reason, because the union operator is not just commutative, but it's also associative. So even if you have, let's say, 3 sets and you take the union of those 3, it can be written also in terms of a union of 2 sets. So that is the first, and that would be actually the second, right? So what is true actually for 2 sets is also going to be true for 3 or more, provided that basically the number of sets that are considered is finite. All right, now but it's not going to be true if you have countably many. So in case of countably many sets where this supposedly be true, you talk about sigma additivity. So anytime basically you see the term sigma in those definitions, right? This means that you have something which is supposedly be countable. Okay, so you have basically in this case a countable union of those sets. And let me remind you, so because you have countably many sets, so the union of countably many sets, whatever that is, including the limit, by the way, supposedly be equal to the sum of the images from those sets. This is basically sigma additivity. Now, this is not going to be an implication of finite additivity. If you have actually sigma additivity, then you also have finite additivity. But if you have finite additivity or / pairwise additivity, you're not necessarily having sigma additivity. We talked about that issue last week, and that's going to be the same thing as well. You raise your hand, sorry.
What is the image again?
The image is when you put something into the function, you call it the image, right? So I'm not sure if you basically, okay, let's discuss that. So I'm going to give you something which you're familiar with. Let's say you got a function, let's say fx equals x squared, right? So that is basically a function. Now you call basically what you put into the function, that's to be the argument. Okay, so that is the argument. And then the image comes out. So what you get out is going to be the image, right? So x is assigned basically to x squared. So x squared is going to be the image of x. Let me just basically give you a specific example so then you see basically what these things are. So for example, when you put, let's say, 2 into the function, okay, you're going to get 4. So then you say that the image of 2 is 4. You understand? So that's basically it. So image of 2, okay? 2 is the argument that you put into it, is 4. Is this understandable? So that's basically, the image is what comes out when you put something into the function. Is this understandable? Now there's also the term pre-image. I'm not sure if you understand that one. So in case of a pre-image, you ask yourself, what do you need to put into the function to get something out? So I'm going to talk about that as well. Let's see, okay, if you understand the term pre-image, okay? Pre-image, in German it's called Urbild, that's a term, okay? So what is the pre-image of 4? Okay, I'm discussing that. So what is the pre-image of 4? In this case, you would need to know what to put into the function to get 4 coming out, okay? There is 2 options, by the way. So I think you understand that, right? Either you put 2 into the function, because 2 squared is equal to 4, or you put negative 2 into the function, because negative 2 squared is also going to be equal to 4. You understand what I'm saying? So that's going to be the pre-image. And the pre-image is a set. Now, of course, there is definitions out there where the images are also considered to be in form of a set, but the pre-image is usually a set if it's not unique, because the pre-image is not necessarily unique. However, the image is always going to be unique. Okay? So there is no argument that can have 2 different images. You understand what I'm saying? Because that's not going to be a function after all. Okay? Do you understand the terms pre-image? Okay, so that's the pre-image, right? So the set containing 2 and negative 2 for that function, for 4. This is it. Now, just a moment. Okay, so the notation for the pre-image is this. Okay, so f to the power of -1, that's just a notation of 4, right? That's a notation of the pre-image. You understand? All right? So you've probably seen this before. Even if the function x squared is not bijective, it doesn't really matter. It can have, let's say, multiple elements that are creating its pre-image. Yes, you... Yes, but the problem is that the function here, x squared, is not necessarily invertible. Okay, so a function is not necessarily invertible. I mean, it is if it is bijective, but it's not necessarily the case. Okay, so x squared is not a bijective function. That's not the one-to-one relationship. Okay, because then the pre-images must be also unique. So if the pre-images are unique, then it's going to be the case, right? But that's not. Okay, so that is actually here. You understand these things, guys? Okay, I hope you do. So if I talk about images, this means that I have put something into the function, and the things that are coming out are the images, right? So when you consider basically the area function or so, this is basically the image, right? Okay, so when you put the union into the function, you're going to get something out. And that's going to be the image of a union. And the image of a union must be equal to the sum of the images, right? If provided that the sets from which the union is consisting of are pairwise as disjoint. If this is true, then this is going to be an additive function, which is basically not just that, but sigma additive if you have counted the many sets, which must be the case also for so-called probability measures as well. So that is actually also true for probability measures in general. Probability measures are sigma additive functions, by the way. But I'm going to discuss that. Okay? Now, based on that, again, I'm going to, let's say, summarize these things. Pairwise and finite additivity are equivalent, just as, again, closure under finite unions / closure under pairwise unions are. We discussed this last week. So if one is true, then the other is also true. And the reason for that is because the union operator is associative, right? I talked about that before. So you can express a union of, for example, 3, 4, or more sets also in terms of union of 2. Okay? You don't need to basically do an actual job. So that can be shown relatively easily by using complete induction, by the way. And the second part is this. Now, pairwise unions and finite unions, however, do not imply actually sigma additivity. So if a function is sigma additive, then it's going to be also finitely and / pairwise additive. But if a function is pairwise additive, this is not going to imply sigma additivity in general. Okay? Now, since basically the sigma algebra is closed under complementation and countable unions, okay, it must be actually, when it's proper, it must be actually sigma additive, however, but this is basically the case. Now, if a function is sigma additive, then it's going to be finitely and as well as pairwise additive as well. Okay, so this is just a summary. Okay, so that's just the same relationship as when we're discussing closure under set operators. Okay, so especially closure under unions. All right. Okay, now, based on that, we can define basically what this would be. Now, I'm going to discuss an example here. So, for example, I'm going to discuss other properties if there is at least one set, which means that at least one or more, right? At least one means one or more, with a finite image. What does that mean? So that basically if the image, let's say, I'm calling the set A, and if you put that into the function, you have something finite coming out. Finite means it's not infinite, right? So this is not going to be infinite. Now, the notation if something is finite is like this, less than infinity, right? That's the notation. Of course, infinity is an abstract concept, but if it's less than that, it's something finite. No matter how large it is, if it's finite, right? That's basically the issue. Now, if there is at least one image in the family that has a finite image on that function, which is sigma additive, So provided that the function is less even pairwise additive, then the image of the empty set is going to be 0. I'm going to show you that one. You raise your hand. So.
Quick question, just for the formality.
Yes.
If we say delta and then such, does it mean
Delta? I didn't say delta.
No, the first symbol.
Sigma.
Sigma. No, the lambda.
Lambda. All right. Okay. There is a lot of letters, right? Okay. Now lambda is the function. You see, that's a function.
Okay. So this could be, for example, x squared, and the things that we are setting in are sets. So basically, we could.
There are sets. Yes, exactly.
And in the set, maybe there could be like 3 or more countable many numbers, right?
Yes, it depends. I mean, basically, depending on the sigma algebra, right, that you're considering. So that depends on basically the structure of. I mean, we're going to talk about random events, or basically events that are associated with random experiments. Okay, and the question is what's in the sigma algebra, because that's going to determine, among others, what kind of properties these things will have. But I'm going to come back to that later on. So I understand it's going to be a little bit abstract. But what you put into it are going to be subsets of the sample space. That is true. And again, I'm going to define what probabilities are. And basically, probabilities are going to be specific functions on sigma algebras created over sample spaces. And sample spaces are going to be actually sets containing all outcomes of a random experiment. A random experiment is going to be an experiment where there is no visible cause or no visibility between cause and effect. So if the outcome is uncertain, that's going to be random in our perspective. It might not be, because there might be a reason why something is happening as it's happening, but we don't know what the reason would be. Okay, so there is no, let's say, visible causality, but just because there is no visibility regarding that, it doesn't necessarily mean that it's not there. It just means that you don't see it. Okay, so some people argue that there is no such thing as random events, which might be true, but that's a philosophical concept. I'm not going to discuss that, so that's not going to be an issue here. But it's interesting, okay? So I have to admit, basically, this is something to think about. Anyways, so I want to show something else. If there is at least one set which has a finite image, so you have something finite coming out, then the image of the empty set must be equal to 0. I want to show that why this is. So let's say I'm going to talk about the image of a set A, okay? Now, the image of a set A is supposedly, I'm summarizing the claim first. So if this is true, which means that the image is finite, okay, so that basically means that you have something finite coming out. It could be, let's say, large, but it is still, even if it's large, it is finite. Then this implies that the image of the empty set is going to be equal to 0, right? Which is also true basically for probabilities, by the way. But I'm going to talk about that later on, okay? That must be the case. So I'm going to show you why, okay? So let's say you're going to consider the image of a set. Now, a set is always equal to its union with the empty set. So if you basically take the union of a set with the empty set, you're always going to have basically the set itself, okay? So that's not going to change. If you unify something which is empty to what it is, then it's not going to change anything, right? And if the function is actually additive, at least pairwise additive, the image of a union is going to be the sum of the images, right? That's basically what it would be, because these two are pairwise disjoint. So the intersection of the two is going to be disjoint. So since this is the case, I mean, let's say the function is going to be additive, then the image of a union is going to be the sum of the images, of the respective images from the set, basically, by which the union was constructed from. Okay, now these two are equal. Now this can only work, of course, if this is going to be 0, right? Because otherwise it would not work. But if, let's say, this is not finite, then it could work if it's basically the image of the empty set would be something else. You have to have at least one set that has a finite image. And if you have a set which has a finite image, the image of the empty set must be equal to 0. That's it. Okay, so basically, if you have an additive function that has for which there exists a set which has a finite image, then the image of the empty set is going to be 0 after all, because these two are equal, as you saw. Okay, and this equality only works in case, if the two are finite. So if this is finite, and that is of course finite as well, then this must be equal to 0, of course, right? So that's basically the issue. So if any additive function for which there exists a set that has a finite image, this implies basically that the image of the empty set must be equal to 0 after all, okay? And that's basically what I'm going to argue. So this is going to be 0, but again, if the image is not finite, then it could be also something else, okay? Because let's say this is infinity, that is also infinity. Infinity plus something is always going to be infinity, right? So it could be also something else. But if it's finite, then it's not. So if there is a set which is actually having a finite image, you're going to have basically that the image of the empty set is going to be 0. Now, based on that, we're going to discuss actually what the measure is. A measure is going to be, to put it in simple terms, a sigma additive function where at least one set has a finite image, indicating that the image of the empty set is going to be equal to 0. Okay, so for example, the length function, but I'm going to discuss some examples. So I'm going to talk about basically measures. So it's called a measure if it has certain properties. I'm going to basically discuss that because I'm going to discuss how that should be. So it's non-negative, of course, right? There is no such thing as a negative area or a negative length or something, right? So length functions, area functions, stuff like that are considered to be measures. All right, that's number one. Number two, it's going to be sigma additive, and I just told you what that means. If you have pairwise disjoint sets which are countable or can be countable, right? Again, it doesn't necessarily need to be finite. Then the image of their union, even if it's basically looking at the limit of those, is going to be equal to the sum of the images, right? So the function is going to be sigma additive as well. Any measure is sigma additive in this context. This is something that you need to understand here. I'm going to discuss that more in detail, but this is what you will need to address. Now, this means that the image of the empty set is going to be equal to 0. The area of nothing is going to be 0 after all, which indicates that a measure is a sigma additive function for which there is at least one set that has a finite image, right? Okay, so that's basically what it is. These are the defining properties. And it must be non-negative, which means that you only have basically positive or 0 images. But it cannot be less than 0, right? That is also true for probabilities. The probability cannot be less than 0. Okay, so that is also non-negative. You understand the point? So the images are non-negative. If the function is non-negative, its images are. Anyways, that's it. And then if you want to consider basically the term probability measure, there is also one defining property that must be also true, which means that the image of the sample space over which the sigma algebra was created from, so keep that in mind when you're looking at it, right? Sigma algebra A is based on the sample space containing subsets of the sample space. Now, if the image of the sample space, in addition, is equal to 1, then we talk about a probability measure. That's it. So lambda is going to be a probability measure in this case. Is this understandable now? All right? Okay, so actually, a probability measure is a measure for which the sample space has the image 1. That's it. Okay? And that is the definition of it. Okay, now, usually when it comes to probability measures, we use the letter P. Okay, so when I look at probability measures, I use P, sometimes with the math call notation. Okay, so when you open your slides, I changed that, but unfortunately didn't have time for the presentation. Anyway, P is P, so I don't care if I declare it to be the probability measure. I mean, you could call it anyhow. There is no mandatory notation here. Omega is supposed to be, again, the sample space. A is the sigma algebra over that sample space containing all events, right? So the elements of the sigma algebra, which is a family which is closed under complementation and countable unions, right? That's what the sigma algebra was. Are called events, so containing all events, right? Subsets of the sample space, to put it in simple terms. But not every subset is basically an event. We discussed this last week, so please watch it again. And if you put those things together, you're going to have a so-called probability space. A probability space is just actually consisting of a sample space, which is here. You have a sigma algebra based on the sample space, and then you have also a probability measure, and putting those together, this creates a so-called probability space. If you talk about a so-called probability measurable space, then the probability measure might not be there. But if you have just that, there would be actually the possibility to create or construct a probability measure on that. Okay, so basically on that set. So that is probability measurable space, but we usually also have a probability measure. So why would we talk about probabilities if you don't have a probability measure? That's it. And again, a probability measure is a measure for which the image of the of the sample space is going to be equal to 1 by definition. All right? That's pretty much it, guys. Okay, now this is technical, I understand, but we're going to need that stuff when it comes to stochastic processes. I'm going to discuss those as well. Anyways, all right. So when we look at measures, and that's basically what you're going to need to understand here. If a function is a measure, then what? Okay, we're going to have also some definitions based on that. Now, there is an important, it's not a remark, it's actually a definition, but who cares, right? So this comes next. We're going to talk about certain properties. So if a property, all right, okay, no, that's the other one. If, let's say, A is a subset of B, and what I assume is that both are elements of the sigma algebra respectively. Okay, so both are events. So one event is a subset of the other. You could imagine. Then what? This means that basically what you have is that the image of the subset cannot be greater than the image of the superset. So for example, the area of Germany, okay, or the area of Frankfurt. Frankfurt is a subset of Germany, right? You can call it like that. So the area of Frankfurt, whatever, however large Frankfurt is, cannot be greater than the area of Germany. You understand the point? If it was, then it would not be a subset. You understand the point? So that's basically intuitively clear. You should basically just address that. So that's nothing else, right? Okay? So if A is a subset of B, then the image of a subset cannot be greater than the image of the superset, right? Because B is going to be the superset. Anyways, okay, so next, there is actually the so-called addition theorem, or different names. You have that inclusion-exclusion principle, giving you the ability to calculate image of unions of any sort, not just unions where the sets are pairwisely joined, but the union basically for any kind of union there is. This is going to be the sum of the images, okay? So you might be familiar with that, minus actually the image of the intersection. Keep in mind that the intersection is also going to be an element of the family of the sigma algebra, because we have seen last week that if a family is closed under complementation and closed under countable unions, then it's going to be also, or is closed under countable intersections as well. Okay, so if two sets are element of the basically of the family, then their intersection is going to be also an element of the family. We have seen that. Okay, so it must have an image. Now, this means the following. Again, this is not difficult to see. So for example, when you look at, okay, so let's say this is omega, you have set A here, and then you have set B. Okay, and you want to basically calculate the area of the union. This is going to be the union of that, of course. This is equal to actually the area of A. So you single out A, which would be here. So that would be actually the red one. This is the area here, including the intersection, of course, plus the area of B. Now, if you basically look at that carefully, okay, so this is B, this is A. What you see is that, of course, you had the intersection twice. Okay, so the intersection, sorry. I'm going to use a different color. You might see it better here. This is actually B, right? I'm not sure if you see it. And if you take the red area plus the blue area, that's not going to be the yellow area on the left, because if you see that, this is larger than that, because you had the intersection twice. So you need to take that out. Okay, there is no such thing as, you know, adding and subtracting Venn diagrams. You probably had that, but you need to take out the area of the intersection, which is going to be the green one. You understand the inclusion-exclusion principle now? Okay, so area is typically also a measure. And when you look at that, this might be consistent. So then, of course, when it comes to the intuition, you might understand this better. All right, next, I'm going to look at basically another thing. So if A is a subset of B, then actually the image of B minus A, or B without A, is going to be just simply B, the image of B minus the image of A. This is also clear, right? Okay, so which is going to be absolutely clear because the sum of the two are, right? So that's basically that one plus that one equals that. Okay, so that's also true. And yeah, so then of course you also, I mean, you had sigma additivity. This is also true no matter what. So any measure is going to be sigma additive. this is true across the board. So the sum, the image of a union is going to be equal to the sum of the images if the sets are pairwise and disjoint. Now there is another property which I'm going to address here, which is called sub-additivity. Sub-additivity holds for every kind of union, whether the sets are pairwise disjoint or not. This is not going to be an issue. This means that the image of a union cannot be greater than the sum of the images. Okay, that's also true. I mean, you saw this from the Venn diagram. So the blue area plus the red area cannot be greater than actually the image of the union, which was the yellow area. So if you rewind this, you can watch it again. You'll find that clearly this is going to be true. Or the actually of the area of a union cannot be greater than the sum of the areas of the respective sets. Whether basically the sets are pairwise disjoint or not, that doesn't matter. So that's called sub-additivity, right? Because you have, okay, inequality sign here as well. Okay, so it's either less or equal, but it cannot be greater. So the area of a union cannot be greater than the sum of the areas of the respective sets from which basically this is constructed from. Okay, that's also provable. So these things are true across the board, and that is also going to be true for probabilities. I'm going to use that quite frequently when I discuss. Okay, so that property is actually important. So I'm going to use that when I discuss basically certain things like convergence and probabilities and whatever. Okay, so then this means, for example, as an implication that, let's say, if this is equal to 0, then that must be also equal to 0, right? In general, okay, if you basically just discuss that. Or if it converges, the right-hand side converges to 0, and so does the left, okay? Because it cannot be greater than that. Anyways, okay, but that's pretty much it. Now, I'm going to also look at the case where I was looking at the so-called length functions. The length function or the area function and so forth are also known to be the Lebesgue measure. Okay, so the Lebesgue measure is the Lebesgue function is a Lebesgue measure, but not every Lebesgue measure. That's French mathematician, right? This is his name, but I'm not going to mention that one because you're going to freak out when you Google it. So basically just take that as is. Simple length function. I'm going to discuss basically the length of closed intervals, which is intuitively clear. Okay, so let's say if the lower endpoint is A and the upper endpoint is B, you would define that to be actually just simply B minus A. Right? That's not difficult to understand. So if there's an interval between, let's say, 0 and 5, the length of that, which would be the image, right? The length of that is going to be equal to 5. Everybody understands this. Now, this is not difficult, okay? So that's for sure. But you would need to also address, for example, the length of open intervals, because open intervals are also elements of the family. So when you define basically the length of closed intervals, how would you also declare basically what open intervals, or how would you actually do the open intervals or the length of open intervals? So I'm talking about basically that. So when I'm discussing open intervals, right, if the interval is open, right, what would be the length of an open interval? And I'm going to show you that the length of an open interval here is just as large as the length of a closed interval. Even if you take things out, the length would not change, which is not intuitive. But why would it change, right? Because that is also an issue. Now I'm going to use something which is referred to be as so-called sigma continuity from below. Okay, so that is going to be, that is also property, but I don't want to basically to create another remark based on that. And this allows me just to address basically the length of open intervals as well. Keep in mind, last week we saw how could we basically create open intervals from union or the limit of union of closed intervals. I'm not going to do that again, so you can basically watch the slides, but when I was basically I was using this example actually. So I was taking the limit of a union of those closed intervals. Those two are actually equal. Okay, so I would need to address basically what this means, because this set again is equal to that. This is what we saw in last lecture. Okay, so during last lecture we discussed this one in detail. I cannot do it again. Okay, now the question is, how would you basically break that down? Because the issue is these intervals from which the union consists of are not pairwise it is joined. Okay, so the union, actually, the image of the union is not going to be equal to the sum of their images in general. So the question is, how would you basically bypass that? And the answer is by using the so-called sigma continuity from below, which is a property that actually every measure has. So this means the following: if the intervals from which the union consists of are strictly increasing, which they are, okay, so as basically the index grows, the intervals are going to be actually greater all the time. Okay, so one is going to be a superset of the other. Now, if one is a superset of the other, why would you take them out, right? Because you would just need to look at the last one. And if this is the case, then this property will allow you to do the following. So you would actually calculate the image of the limit of the union is going to be the limit of the image. Point blank, period. That's basically what it is. So keep in mind, this is basically what sigma continuity allows you to do. Okay, so sigma continuity means, just to put it in simpler terms, that the image of the limit of a union of strictly increasing intervals, let's say, or strictly increasing sets, which means that the next one is going to be the superset of the other, is going to be the limit of the images of those sets. Okay, and that's pretty much it. So this allows you basically to bypass the image operator by the limit operator, simply. All right? Now, why this is, again, I don't have time to consider it. It's not that important, okay? But it simply claims that the limit, the image of a limit of a union is going to be equal under this consideration, or under this circumstance, to the limit of the image, or the limit of the images of those sets, right? And that's it. And we know basically how to create, or how would you basically calculate the length of a closed interval. You subtract basically just the two, but I'm going to look at the limit of that. Okay, so you can already discuss that, because you would take the upper endpoint minus the lower endpoint, and then the limit based on that, but you won't need to do this. You can also address this directly, so that's going to be actually what the limit, you would need to look at what the limit of the lower endpoint and what is the limit of the upper endpoint. Now, if n tends to infinity, this means that 1 by n is tending to 0. So that's basically what it's going to, you end up with. All right, so the limit of the yellow expression, just ignoring the image, is going to be a, because 1 by n is going to tend to 0, and the limit of that one is going to be b, because again, 1 by n tends to 0, right? Okay, and as you see, and this is basically what the lesson to learn here, the length of an open interval is equal to the length of a closed interval. So even if you take things out, okay, that takes things out, it doesn't necessarily mean that the length of it will going to change, especially when you look at basically single elements, right? And I mean, it is also intuitive, because the length of a single element, right, which is also Borel set, by the way. Borel sets are, remember what Borel sets are? I didn't mention this before, but the Borel algebra is the algebra that, or sigma algebra, apologize. I mean, okay, every sigma algebra is also an algebra. But anyway, so this is the sigma algebra that is generated from open intervals on the set of real numbers. Okay, and that's basically interesting. Anyways, yeah, so this is basically what it would be. Okay, and yeah, so that's it. Okay, so that basically the length function is actually consistent also for open intervals. Now, if you want to define, basically do this differently. So let's say you want to define, because Borel sets are generated from open intervals. So you could start there. Okay, so you could basically, I mean, this makes more sense, because again, Borel sigma algebra is a sigma algebra that is generated by open intervals, but it's equal to that of closed intervals, let's say. So you start from here, and then you would basically try to address what the length of a closed interval would be. That's going to yield the same, and the so-called sigma continuity from above allows you to do that. This is going to be the same, or basically the mechanism is going to be the same at least. So that's going to be the following. Okay, now first you should need to see that this is going to be the closed interval is going to be the limit of the intersection of those open intervals, right? So that's basically what, just a different perspective. These open intervals are strictly decreasing. So the next one is always going to be a strict subset of the former, whereas the former was the superset of the other. Okay, so those intervals are going to be actually decreasing. If that's the case, and that is basically what it is here, okay, then sigma continuity from above would claim that the image of the limit of the intersection of these decreasing intervals is going to be equal to the limit of the images of those intervals. Point blank, period. Okay? And since we have defined the length of open intervals over here, the upper endpoint minus the lower endpoint, although basically both the lower and the upper endpoints were excluded, you'll find, and that is also going to be the same principle, you'll find, okay, since 1 by n is converging to 0, as n tends to infinity, of course, that this is going to be actually the length of the open interval as well. So you can just summarize that actually the length of a closed interval is just as large as the length of an open interval. Now that doesn't mean that for probabilities that's going to be the same thing. Again, I was just talking about the length function. The length function, whether you find it on basically on open intervals or closed intervals, it doesn't really matter because one implies the other. Okay? But that's just something which I wanted to stress here. So just because you're taking out something from the set, it doesn't necessarily mean that the set is going to get smaller in terms of its length, okay, or in terms of its size, which is actually not intuitive, but as you see, this is basically what it would be. Because the length of a single element on a straight line is always going to be 0, just as the area of a straight line is going to be equal to 0 as well. Okay, so when it comes to basically higher dimensional case. Anyway, all right, so that's something you should basically you should be aware about. Now, I'm going to, and that's basically what I wanted to tell, I'm going to define what a property is that holds almost everywhere. People are kind of struggling with that concept, but I'm going to use this very, very, very often. So after a while, you're going to get used to it, okay? Now, of course, there is a measure based on that. So whether this is a probability measure or another measure, maybe it could be the length function, it doesn't really matter. A property is set to hold almost everywhere if the length or the image of the set for which the property does not hold has the measure 0. Okay, so let's say, okay, I'm going to start from scratch. If, let's say, lambda is a measure, what is a measure? A measure is a non-negative sigma additive function, right? For which the image of the empty set is equal to 0. So if that's true, okay, that was the measure based on a sigma algebra, then a property is set to hold almost everywhere. Almost everywhere, okay? If for all sets, or for all elements given in a certain set, so for all elements of a certain set A, where A is, of course, an element of the family, right, on which the function is defined. If the complement of that is having a measure which is, or image which is actually equal to 0. So if any set has an image 0, it's going to be called a null set. So null set is a set that has an image 0. And if the complement of that is going to have an image 0, then we say that the property is true almost everywhere for the elements from the set A, from which the complementation was considered. If you're not sure you understand this, I'm going to take some examples after all, so you see what this would mean. Okay, but I'm going to use that very frequently. So for example, Wiener processes, blah, 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 are continuous almost everywhere. And you should also understand what this means, so I'm going to basically discuss that in detail. Okay, so notice that basically the complement is not necessarily empty. Okay, you might not find that basically intuitive, but I'm going to basically just discuss examples you might be familiar with. So I think you saw this. Now, if it's a length function, okay, it's not necessarily the length function. It can be also a probability measure, but if lambda is the length function in particular, so the Lebesgue measure, that's how you call it, then what's interesting here is that the image of every countable set is going to be 0. Okay, so if the set is countable and you want to take the length of that, What does countability mean? Countability means that you can express the elements of the set by a sequence. This is what a countable set is. If you can, so if there is a possibility for that, to do so, then the image of that is going to be 0, if you consider just a length function. Now, however, this is not necessarily true for every probability measure there is, especially not for discrete random variables, so you might be familiar with that. But if you just talk about the length function, and that can be shown easily, okay? I mean, just let me remind you why. Okay, so just give you a little intuition why. Let's say you want to calculate, for example, the length of a countable set, where the countable set consists of the elements A and B. Okay? So that's something you could do. Now, how would you get there? You need to understand that this is going to be, I mean, the same as the length of the open interval, I'm going to start from behind. The length of a closed interval from A to B, taking out the open interval. Okay, so minus the length of the open interval. Okay, from A to B. Okay, so the blue one is the closed one, and the yellow one is the open one. And we saw that their two are equal. So that's going to be actually equal to 0, right? And this is a countable set. And as you see, the set is not empty. You see? So it can have the length 0, which it has. And that is also true, but for every countable set there is. So that is also a Borel set, by the way. Because the difference of two Borel sets is also going to be Borel set. And keep in mind, the yellow one, the open one, is a subset of the blue one. All right? Okay? So that is, again, this is also referring to the property that we just discussed. Okay? So the length of every countable set, when it comes to basically the length function, right? The length of every countable set, even if it has infinitely many elements, is always going to be equal to 0. You understand the point? Okay? So that is not a contradiction, guys. So just because, let's say, the image of a set is going to be 0, it doesn't necessarily mean that the set is empty. Okay? That's what I wanted to basically to stress here. All right. So, okay, I'm going to, again, talk about that in a, let's say, more different context, but you'll see basically, I'm going to talk about continuity almost everywhere and all that stuff, but let's say, I'm going to basically also define what almost sure events are. So this is based exclusively on probability measures. So you don't have anything else. So if P is a probability measure, and let's say the complement of an event is actually having a 0 measure, okay, which is also not necessarily empty, by the way, especially when it comes to so-called continuous random variables, then we say that the event A is happening almost surely. But it doesn't necessarily mean that it will, okay? Okay, so just because an event has a probability 1, it doesn't necessarily mean it will happen. I'm going to give you an example from that. So at the beginning, for me, it was very difficult to understand, I have to admit, so I had to spend a lot of time thinking about this. But that's how it is, okay? So there is, again, okay, we're going to do some applications too, but the applications needs to be consistent, so I'm not supposed to have any contradictions based on the definitions that I'm providing you, okay? Now let me just consider examples. Now, one of the things that I want to mention is this: if the complement, the probability of the complement is 0, then of course the probability of the original set is going to be equal to 1. That is for sure. So actually, an event is set to happen almost surely if it has a probability 1. Okay, but just almost surely. Keep in mind that the event itself, so A, is not necessarily equal to the sample space. Of course, the image of the sample space is always equal to 1. Okay? But A can be a strict subset of that. Again, okay? It's not necessary that the complement is empty, as you would see that for the length function. Now, you solve this basically for the length function, but I'm going to provide you with an example you might be familiar with. So when it comes to, let's say, a continuous distribution, let's say X, you're familiar with the normal distribution. Probably seen that before, Okay? So let's say x is even standard normal, but it doesn't necessarily mean, I mean, whether it has mean 0 and variance 1, it's not necessary. Have you seen this before? Okay? All right. Okay, so let's say that. Now, for any continuous variable, let's say I'm going to define an event for which basically I declare x not to be equal to a. Okay? And I would say that this happens almost surely. Okay, so then it can be shown that the probability of the complement is 0. That is true for every continuous random variable. Okay, so and that is also true for the normal distribution. So this means, on the other hand, the probability that a normal variable takes a specific value, let's say, I mean, it could be a, but it doesn't really matter, is going to be 0. Okay? You understand the point? That's basically it. So the probability that this is not going to happen is going to be actually equal to 1. Now, whenever I see basically the description that, you know, the sample observations are coming from the normal distribution, okay? So when it comes to basically applications like asset pricing and so on, there is a standard assumption that asset prices do follow the normal distribution, for example, but that's a contradiction in itself, okay? Because the probability that a specific random variable takes a specific, a continuous random variable or normal random variable takes a specific value is always going to be equal to 0 no matter what. So it would be actually technically impossible to observe the sample that you have. But you do have it. You understand the point. And that's the issue. But it's actually, you would say that it's not going to happen almost surely. That's the issue. Okay? So basically the assumption that sample observations would come from the normal distribution is a contradiction in itself. Because the probability of that will be equal to 0. But it's still there. It happened. You understand the point? So just because an event has a probability 0, it doesn't necessarily mean that it's not going to happen. It happened, right? If it's true. So if your assumption is true. You understand the point? All right, so this is basically what it would be. So you can say, if this is the case that the normal variable is not going to be a almost surely. But it could be, right? Because otherwise it would be impossible to observe the normal distribution. You understand the point? Okay? I found this very fascinating because I had to think a lot about it when I saw this for the first time. But that's how it is. This is also true even if you define another event. So that's another example where you would basically assume that x would be something, an element from the real numbers where you would take out the rational numbers, which is basically the set of irrational numbers. Okay, so the probability of the event that x is going to be irrational. And the complement of that, so what would be the complement of that? This means that the probability, I mean, again, so I'm going to translate this here. This means that the probability that x is rational. So x is going to be an element from the set of rational numbers, which is denoted by q. Now, q is a countable set, right? So that's going to be also 0. You understand the point? Okay? Because it's countable in this case. So the probability of x taking any value of a countable set is going to be 0 if the random variable is continuous, especially for the normal distribution. That is true. Okay? Well, so you would argue in this case that x is almost surely irrational, which means that it is not rational, right? Okay? That's basically what it is, but how am I supposed to say it otherwise? Okay? Okay, but that's it. Now, if basically lambda, I'm talking about in terms of the length function here. So if we have the length function, then we also can say that the length of the set of rational numbers, as I mentioned before, because that's a countable one, is 0. So almost all real numbers are irrational. So there is basically the issue that there are more irrational numbers that are rational ones, because a set of irrational numbers is not countable. And a set of rational numbers is. We saw this last week, okay, in that sense, okay? So the length of that is going to be 0. If a set is countable, it's always going to have its length or area, whatever basically the setup is. In this case, if it's a length function, the length of the set of rational numbers, which can be constructed, by the way, okay, based on properties of measures, is going to be 0 after all. Okay, I'm not going to prove this, so if you want to check out the proof, I'll put it into the reader, but you will not need it for the exam, so you can just skip it. If you're interested in it, I will prove that there, okay, but I will not going to present this. Now I'm going to talk about measurable functions. Measurable functions are not directly linked to measures, only maybe in the case of random variables. So random variables are going to be so-called measurable functions. Now, for a measurable function, what you have is, I'm going to call them x. So you can associate it back with random variables because, again, random variables are measurable functions. Actually, just a special case of measurable functions. You need two sample spaces. One, okay, is called omega 1, and the other is going to be omega 2. And we are going to assign elements from omega 2 to elements from omega 1. Okay, and a function which does that is not necessarily a measurable function. Okay, so it has to have also certain properties, but you need to understand that there is, again, a so-called measurable space. Okay, so there are two measurable spaces. Again, the purple one and the blue one both are, and there is sigma algebras over those measurable spaces. And x, capital X, that assigns elements from basically from omega 1 to or onto omega 2 is going to be called a measurable function if the preimage, and there it comes again, the preimage, right? So we talked about that, what it was at the beginning. The preimage of every A2 measurable set. What is that A2 measurable set? What does that mean? This is a set that is an element of the sigma algebra A2, okay? So the preimage of that, I'm not talking about the set, I'm talking about the preimages, okay? So all preimages of those sets must be, and this is basically what I'm going to address here, must be elements, okay? So if a set is A1 measurable, that this means that is an element of the sigma algebra 1, A1 must be an element of that sigma algebra, otherwise it would not be the case. I'm going to, okay, so I think this is a little bit more complicated, but I'm going to use examples to show you that basically what the measurable function would be. So especially the term preimage is going to be an important one. So the preimage of every A2 measurable set must be an element of the sigma algebra A1. And that is, if that's the case, then you'll have a measurable function. Now, a random variable, and this is basically what is going to be, is associated with a probability measurable space, and the other is going to be actually the Borel measurable space. Okay? So a random variable is going to be, and this is something which I'm going to stress here, okay? So x is the random variable, so that is supposedly be the case. It must be a so-called measurable function. Now, what does that mean in this case? Now, let me tell you what the random variable does first before I address the property that comes here. What the random variable does is it assigns real numbers to outcomes of the sample space. Keep in mind, omega is the sample space, and the sample space contains all outcomes of a random experiment. So a random variable is actually a function that depends on outcomes of a random experiment, right? So you can say that it's a real number that depends on outcomes of a random experiment, okay? So it is a real number without loss of generality, by the way, okay? There is complex random numbers, but I will just fix on, I will consider only the ones that are real, okay? Now, a random number is actually a function of a real number that is a function of outcomes of a random experiment. That's it, with a certain property that is described here, but I'm going to talk about that. So a real number depending on, let's say, something random is a random variable, okay? I mean, that makes sense, but it has to fulfill another property, which is a little bit more technical. So this means that the preimage of any Borel set, on any Borel set, must be inside the set of all events, which is actually the sigma algebra A. So the sigma algebra A over the sample space contains every single event there is, okay? Which is, again, the set of subsets, specific subsets, over omega. Now, if you're not sure what this means, I'm going to use an example whether I would, again, so there is discrete random variables and there is continuous random variables. And there is, of course, the third category, which is neither. We call a random variable discrete if the set of its images or realizations is countable. That makes sense. For example, the binomial distribution, the Poisson distribution, things like that. Okay, have, let's say, countably many outcomes. Okay, so the images which come out. Okay, here the issue, what the image. Okay, so you have real numbers coming out, so which are random. That's basically the simplest way to explain this. But it's a little bit more technical, so again, what this means, I'm going to illustrate that using examples. So if you're not sure, I'm going to tell you what it means. Okay, but you know what a Borel set is. A Borel set is an element of the Borel sigma algebra, and a Borel sigma algebra, on the other hand, is a sigma algebra that is generated from open intervals on a set of real numbers. Now again, in practice, there is two categories, discrete and or continuous ones. Okay, but actually in theory, there is also the third, which is neither, but I'm not going to discuss that. Now, for continuous random variables, it's typical that the set of basically the images that come out, the set of realizations, is not going to be countable. But just because the set is not countable, it doesn't necessarily mean that the random variable is going to be continuous. So this is just necessary, but not sufficient for the random variable to be continuous. Okay? Keep that in mind. So people tend to associate it with these things with each other, but that's not necessarily true. For discrete ones, there is. So if the set of its realizations is going to be countable, that is going to be a discrete random variable, no matter what. Even if basically the sample space is not countable, it don't matter. Okay? If the outcomes are, then it's going to be discrete no matter what. So the outcomes of the outcomes of the images, I'm going to call them images so not to confuse you, the images or / realizations of the random variable are countable, then it's going to be discrete, point blank period. And if it's discrete, it's going to be countable. So that's a one-to-one relationship. Okay? If you're married to someone, then this person is also married to you. Okay? So if the set of its realization is countable, then it's going to be discrete. If it's discrete, then basically the set of realization is going to be countable. But that's not true for continuous ones. Okay? So regarding continuity, this is just a necessity that basically the set of realizations is not countable, but not a sufficiency. So just because it's not countable, it doesn't necessarily mean that the random variable is going to be continuous. Keep that in mind. But in practice, it is. So when it comes to applications, there is just these two. Okay? We don't distinguish between. I mean, the third type is not relevant from the practical perspective. From the theoretical perspective, it's going to be still important because you might have some contradictions here. Now, if you want to examine whether the following function is going to be a random variable, so let's say I'm going to give you the outcomes of random experiments shall be A, B, or C, okay, whatever it is. And I'm going to define a function. Okay, there is a sigma algebra, which I need to address here, containing the empty set. Again, we've proven that last time that the empty set must be always an element of the sigma algebra, so is basically omega itself. I'm going to take another one. So for example, the set containing A and B is also there, let's say, and the set C, which is the complement, by the way. So this is the complement of that set. I think you see this, all right, with respect to omega. And omega must be also there, so that's a relative small one, but anyway. And I'm going to, let's say, create a function based on outcomes of the sample space or the outcomes of a random experiment. So let's say the image of A. So if A happens, then the random variable should be equal to 0. Or if it's a random variable, I mean, it's not sure, so keep that in mind. I want to examine whether this is the case. The image of B shall be equal to 4, and the image of C shall be equal to 5. Okay, that's a simple one. All right, and I want to basically examine whether the random variable, the function is a random variable or not. And let me tell you this, it's not going to be. Okay, why? Because, and the simple answer is because not every pre-image of every, there is at least one Borel set for which the pre-image of that Borel set is not going to be an element of the sigma algebra A containing all events. Okay, so that these are the possible events that can be basically addressed. Again, so this is basically the question that I'm going to ask. Now, I would need to basically look at the pre-image of certain sets. For example, again, I'm going to the question here is equivalent. So if it's a case, then the pre-image of every Borel set must be an element of A. And if every pre-image of every Borel set is an element of that, then this is going to be the random variable, and I'm going to show you that this is not the case. So which means that there is at least one Borel set for which this is not true. Okay? Now, I'm going to create basically that, so I want to know what the preimage of that is. Okay? Now, it must be something, basically, or a subset of omega. Why? Okay, it's because I want to, I don't know why people are basically kind of bothered here. So what's going on here? And, you know, I'm going to open it and check it out what the people are doing. Okay? Open, close, okay? This scares them off. Anyways, okay, now what do we need to have is this. It must be an argument, right? So this is, I mean, I'm referring to it as a set of all arguments, which must be actually elements of the sample space, right? For which the following property is true. The image of that argument, which is part of the preimage, right, of the function, must be an element of this interval, okay? Now, I'm going to address this. So the question is, when do you have 4 or 5 coming out? Because this is the only possibility to get something which is inside that interval. And the answer is if you put in B or C. Okay, so if you put in B, you're going to get 4. And if you put in C, right, you're going to get 5. So the set containing B or C is going to be the element, or basically the preimage of this set. And now you see clearly that this is not an element of the family, right? Because it's not there, you see? So that means that not every preimage of every Borel set is measurable with respect to the set of all events. You see? So that's it. That's it. Okay? So, of course, it's much easier to show that something is not a random variable rather than it is. Okay? But I wanted to take that as an example so you see basically, so the preimage of this is a Borel set, by the way, right? So that is a Borel set, of course, right? Obviously. But the preimage of that is not an element of the sigma algebra A. And thus, X is not a random variable from the technical perspective, although it assigns real numbers to outcomes of a random experiment. But from a technical perspective, it's not going to work, because the problem is, I want to know, for example, what the probability of the random variable taking values between 4 and 5 would be, and I simply cannot do that, because for probabilities, a probability measure, okay, and that's maybe you remember, is a function based on a sigma algebra. Okay, so whatever that I'm putting in, it must be an event. And then you have actually real numbers coming out. In particular, when it comes to probability measure, you're always going to have something between 0 and 1. Okay? All right, so that's actually it. So that is technical, I understand, but I want to be consistent regarding definitions. So I wanted to give you an example of that, but again, it's much more difficult to show whether a function is that a function is a random variable rather than it is not. Okay, so you just need one example to blow it off. Anyway, so let's say it is. Okay, so let's say you got one where this is true. So the preimage of every Borel set is going to be an element here for that. You got a probability space, and then you have basically a Borel measurable space. Again, in Borel, it's just simply measurable because a measure is not included, but it could be the length function that is there. So if you have the length function, then it would be a Borel space. The measurable means that there is a possibility to create a measure on that, but it's not, the measure is missing, so therefore it's not there, right? And let's say I want to know what the probability of that is. Now, the probability of that must be actually the probability of this event, and now you see why it's necessary for this event, okay, to be an element of the family, because the probability measure, again, I didn't write it down here, but maybe you should, is a function that assigns elements of the family, or real numbers, sorry, which are between 0 and 1, to elements of that family. This is basically what the probability measure would do, technically. Okay? So anything that you put into that function must be an event. And it's only going to be an event if it's an element of the sigma algebra A. Because if it's not, then it's not, right? Okay? You cannot basically address the probability of that. Now, you would also say that what is the probability of X being between 4 and 5, which, again, there is different notations of that. And this is actually the definition. So you can see basically clearly that the probability that x is between 4 and 5 is defined to be actually, and if it is a random variable, the probability that the actually, or you can say, I mean, for the pre-image, basically. So the probability that, for the probability of all elements of the event where actually the images of the random variable are between 4 and 5. That's pretty much it. Okay, so that is technical, by the way, but it is still true, and that's basically what it would be. So this is how you would calculate. Now, this notation is not very practical, right? You see this much more often, which therefore it's basically more relevant, but that's actually the correct way to express this. Okay, so the pre-image of every Borel set must be an element or must be an event. That's actually it. Okay, because otherwise it would not be possible to assign a probability to that. Now, if you talk about basically something like this, and this is also Borel set, by the way, which again is corresponding to the set containing just 5. Okay, usually when it comes to an interval, the upper endpoint is strictly greater than the lower. But if that's not the case, you can simply just define that to be. Okay, so sure, that would be the definition here. Apology. Okay, by definition, let's say, which is a Borel set also. Okay, now this means that, okay, x is between 5 and 5, which means that x is equal to 5, right? That's also true. Okay, so in this case, you would write it like this. You could assign that one as well. And here it comes. Okay, so that is actually more common. Let's say I'm going to use that one as well. But this is actually how it's done. Now, this creates actually the so-called probability mass function. And that is going to be important, especially for discrete random variables. So especially for those. Okay, not necessarily for continuous ones, but again, for continuous ones, it's not the use of that. But basically, by definition, the probability mass function of a random variable, let's say at 0.5, will give you the probability that x is equal to 5. Again, and here is, this corresponds to the probability of the event where the outcomes generate that image, which is equal to 5, basically. All right, so that's it. Anyways, okay, so this is just also another definition. I'm going to come back to that here. Okay, so the probability that, let's say, the random variable is between -infinity and 5, or not greater than 5, is on the other hand going to be the cumulative distribution function of that random variable at 0.5. So that is by definition the so-called cumulative distribution function, by the way. So you can just see that one here, okay? So that one, the cumulative distribution function of a random variable at 0.5 will give you the probability that the random variable is not greater than 5. That's it, okay? And you can also use that for every set there is, basically, because the corresponding Borel sets have pre-images that are elements of the sigma algebra A. All of them, okay? If x is a random variable, that must be the case. Okay, that's it. So actually, well, okay, you would see that, okay, and in general terms, the cumulative distribution function at point x, small x, by the way, is going to give you the probability that the random variable capital X takes values that are not greater than that, maybe not greater than small x. You've probably seen that before. And now I'm able to define it. Okay, now I'm going to summarize this. Okay, so that's going to be actually the next one here. This is the definition, cumulative distribution function, which I'm going to call it CDF. Is a very important definition. So that is important, both in theory. I mean, okay, more in theory, but in practice, you don't have that much cumulative distribution functions. Okay, maybe except the normal distribution or the distribution, whatever. Okay, but when it comes to data analysis, you don't know actually where the data is coming from most of the time. Anyways, okay, so that is actually the probability that the random variable of which the cumulative distribution function is considered takes values that are not greater than the argument of the cumulative distribution function of the random variable. I'm going to get some keys. Okay, anyways, okay, I mean, there is a possibility to get out, but not to get in. Anyways, okay, which is, again, if you want to be more technical, Okay, here it is. I mean, that's basically the issue. Okay, so that's a Borel set of which the pre-image actually is taken from. Okay, so here it is, right? And the pre-image of that contains all outcomes that generate images between -infinity and x. Okay, now why is this important? Because any random variable is going to be well defined by its cumulative distribution function. What does that mean? What the term well defined means? This means the following: if you know what the cumulative distribution function is of a random variable, then you automatically know everything, and I mean everything, about the random variable. Okay, so you know what the expectation would be if there is an expectation. You know what the variance is. You know basically what the density is, if there is any. You know what the moment generating function could be. So you can calculate anything which is attached to the random variable if you know what the cumulative distribution function of the random variable is. But it's more important from a theoretical perspective rather than applications. We see that actually only when it comes to applications in context of hypothesis testing. Okay, so then you would calculate basically so-called critical values and p-values and whatnot, and then you would need to have the cumulative distribution functions of random variables. Okay, but most of the time, with simply data analysis, you don't know where the data is coming from. Okay, all right. Anyways, yeah, I mean, there is a difference between applications and theory. The probability mass function, I define it also, is going to be important only for discrete variables. Okay, so a discrete random variable is going to be well defined through its probability mass function. The probability mass function, in contrast, will give you the probability that a given random variable is going to be exactly what the argument of the function is. So the probability mass function at point small x is going to be the probability that a random variable takes that value small x. Okay, and that is also only going to be important for discrete ones, not for continuous ones. If the random variable is discrete, which means that the set of its realizations is countable, then a probability mass function is going to be sufficient for that random variable. So if you know what the probability mass function of a discrete random variable is, then you know absolutely everything about that random variable, but only for discrete ones. Yes? Not necessarily, because the histogram is an empirical distribution. And when it comes to probabilities of, let's say, discrete random variables, that is a theoretical one. Okay? Histograms are actually done for data classes, but that's empirical. It's basically the two have something in common, right? But they're not directly the same thing. Okay, so the set of all probabilities for a discrete random variable could be also displayed by a histogram, let's say. Okay, that is possible, right? But the histogram is basically just an empirical distribution rather than theoretical one. You can call it histogram if you like, but it's not. That's called the probability distribution. That is its exact term. Anyways, yeah, okay, so again, this is only true for discrete random variables. I want to basically stress that because for continuous ones, it is not true. For continuous ones, it's actually the opposite. The probability mass function is going to be 0 at every point there is. Okay, so you don't know what that would be. Now, okay, as far as distance functions are concerned, let's take a break now, and then we're going to discuss that after the break, if you don't mind. I suggest, because I don't have 5 minutes, I'm not going to do that, so we're going to do this after the break. Okay? All right. 50 minutes, if that's enough. All right, so we are going to, okay, well, I have interrupted this. Let me just basically go to the slide where supposedly be. Okay, it was 600 something. Maybe we go back a little bit. I'm going to cut it out. Yeah, distance functions. I see. That's what basically we're up to. Okay, so using that one again, we are going to look at distance functions. So for example, I'm going to define what a distance function could be. Let me just provide you with some examples. It's related to measures also, okay? So we're going to look at distance between two objects, which are both from the sample space, and to be just basically simply the difference between the length of them. So let's say you got a set of real numbers, then it could be basically the distance between two real numbers, just the absolute value of their difference. Okay, so when you look at basically, for example, two different real numbers, A and B, the length, sorry, the distance of them is going to be just the absolute value of their difference. A minus B, the absolute value of the difference is going to be also equal to the absolute value of B minus A. So if you put it the other way around, it doesn't really matter. Okay, now in case of a multivariate issue where you have basically the same two dots in a coordinate system and want to establish the distance between the two, okay, there is also, for example, the Euclidean distance. Now, according to the Pythagorean theorem, if you want to calculate the length of the hypotenuse, you would need to take the square root of the sum of the squares from the two cathetes, right? So the square root of the sum of the squares from the two cathetes will give you the length of the hypotenuse based on the Pythagorean theorem. This is why it's called Euclidean distance. I think everybody knows this. So that could be actually, I mean, if you do that, in this case, it's going to be 5 because 4 squared is 16 plus 9 squared is 25. So the square root of 25 will be 5. So the length of hypotenuse will be 5. All right? But sometimes it's not possible to use the length of the hypotenuse. For example, when you consider the so-called Manhattan distance. I'm not sure if you've been to New York City, but if you go to Manhattan, I mean, this is basically the name, or you look at the map of Manhattan, you cannot cross if you want to go from A to B. You cannot cross it. So you cannot use the hypotenuse in that regard. You need to walk around the blocks. So you would need to basically walk 4 units to the right, and then you would go to the top 3 units then. So that's going to be the Manhattan distance, basically, between the two objects, A and B, within the coordinate system, because there is no possibility to move around. Okay? So distances can be different regarding basically what consideration, what the context is. But in order to define this, again, this is not very easy to do so. You would need to just basically address how they should be. Okay? So that's basically the term that I'm going to use. So when you would have a distance function you need to have 3 properties, basically. You have a Cartesian product of which basically you assign certain non-negative real numbers. Now, if basically the distance between two objects supposedly be 0, that this should mean that the objects are identical. So objects are identical if and only if their distance between them is 0. So if the distance between them is 0, they should be identical in that regard. And if they're identical, they should be having 0 distance between them. Number 2, the distance between A and B should be equal to the distance between B and A. That is also true, right? So that is actually intuitive. If you go from city A to city B and then you go back, I mean, you could use different ways or so, but should be, if you're using the same ways, that should be the same length. Okay, apologize. Okay, sorry for that. Now, that's number 2, sorry. And then number 3, there is the so-called triangle inequality. So this means the following. So when you consider basically the distance between the two objects A and B, which is represented here, so that distance, it could be the length of the hypotenuse that you saw, but it's not necessarily the case. It could be also the Manhattan distance, whatever. This is the direct way between the two. It should not be greater than the distance between A and C, which is here, plus the distance between C and D. So if you go from A to B, okay, this way directly, then the distance between, the length of this basically line should not be greater than the sum of those two. Okay, that is also intuitive, by the way. So if it is, then it's not going to be a distance measure in that regard. But it can be equal. So when you look at, for example, the Manhattan distance, in case of the Manhattan distance, right, it would sometimes be equal, right, because you would need to go to C if you want to go from A to B first. Anyways, okay, I'm going to use that basically to create limits of sequences. Now, this is probably something you saw in different courses. For example, you have 1, 1/2, 1/3, 1/4, and so on. This sequence is converging to 0. I think everybody knows this. Okay, so we call basically limit 0. And the property is that basically the sequence or the members of it can get arbitrarily close to the limit. So that's basically the definition, right? There is a possibility to get arbitrarily close to the limit. Now, regarding the members, the first member, which I'm going to call A1, the second member A2, and so on. So these are the members. And if the sequence is convergent, okay, then there is a possibility to get arbitrarily close to its limit, which is supposedly be A in this case. Okay, but it's not necessary though. So these are just names, by the way. So but that's how it's represented. If you want to denote this, there is multiple ways to do it. One way to do so is basically, you know, I mean, in this case, you could assign what, or you could, I don't know what this is, guys. You could basically also tell what the nth member of the sequence is. In this case, though, it is 1 by n, of course. So the first member is going to be 1 by 1. The second is 1 by 2. The third is 1 by 3, and so on. And you could basically, again, so this is the index, by the way. And then you can express the limits too differently. Maybe I open it, so it's going to get on my nerves. So then people see we're in there. So they maybe want to join. Apologize. I don't know what the people are looking for. Okay. I mean, I do scare them, but this is not something which is supposed to be. Okay. So maybe they see us. Now, representing limits can be actually different. So I'm going to use one hand, basically this is the notation that you're probably all familiar with. The limit of the sequence is A. This is it. Okay, so you can simply just call the sequence AN, which would give you the nth member of that, number 1, or which is in this case 0, or number 2, which is also used very often. So this is something which you're not so familiar with. So the sequence converges to the limit. This is it. I mean, that's basically the same thing. So you can use basically both. Sometimes I tend to use that one. Sometimes I tend to use this notation, which appears to be more practical depending on the context. But I tend to use the latter sometimes because it's actually more accessible. I don't have the limit operator all the time. Anyways, okay, so that's something actually you're probably familiar with. But I'm going to define this anyway. So a sequence is called convergent. Okay, if you have a distance function. So mostly, when it comes to real numbers, so you will basically address sequences on real numbers. The distance function, the most common distance function that we use, okay, so the most common distance function that we use is simply just going to be actually this is what you saw, and that's basically what you will have. The absolute value of their difference. Okay, so when A and B, the objects are real numbers. And this is basically what it's going to be, but it could be also something else. Anyways, so if it's something else, it's not very straightforward. How would you consider it to be a sequence to be convergent? But you need to have a distance function at least. Okay, so that is just actually. Now a sequence, mostly in set of real numbers, is called convergent to the limit A, which is also an element, by the way. So and that's something which I want to stress here. The limit must be also an element here on the set on which basically the sequence is supposed to converge. If, and that is something which is, again, might be straightforward, for any distance, so epsilon is going to be a distance, there is a member which is expressed by the index m. So if I say m, which is of course something which is a set of real number, this is something which is an index, okay, from the sequence. So that identifies a specific member, after which, okay, so all following members have even smaller distances than that. So this means that no matter how close you are to the limit, the following members are going to be closer. This is basically the formal definition that you see. And if this is true, then the sequence is set to be convergent to the limit. You understand that, guys? I'm not sure basically you've seen this before. But again, no matter how close you are, okay, to the limit, there is, after a while, there is always going to come a certain member of the sequence, after which all following members are even closer, okay? And that's basically what convergence is, okay? So you can get arbitrarily close to the limit, basically, because no matter how close you are to the limit, all following members are going to be closer after a certain point, okay? So after a while, sooner or later, okay, you're going to be even closer, okay? And that is something which is supposed to be true. Now, again, so I basically translated that definition. So for all positive distances, no matter how small it is, okay? So all, basically, no matter how small it is, there is going to be a member after, sooner or later, okay, that has an index m, for which after all following members, okay, or our subsequent members, sorry, okay, with indices that are greater than that, okay, so that's something which is here, okay, have distances which are even smaller than the previous one, okay, so they're even closer to the limit. That's it. Okay, so no matter how close you are to the limit, there is going to be a member where all subsequent members are going to be even closer. And that must be the case. All right? If there is a possibility to identify that member after which all following members are going to be even closer, then the sequence is going to be convergent by definition to that limit. Okay? Now the limit must be unique, of course, so there is no actual sequence that have two different limits. It can be shown, you've probably seen this before. Okay, but I'm not going to basically elaborate on those things, which basically I'm not going to use. Okay, so, but technically this is what it means. So if the sequence is convergent, then it can get arbitrarily close to the limit. That's easier to understand. Okay, so if you're not sure basically what the technical definition is, okay, so what this means, just remember that. Okay, and I think everybody has seen this before. Now, based on that, again, I'm going to look at something which is also going to be true. So, not a definition. So, if basically the limit is finite, because you could not say that the limit is not finite. If the limit is not finite, that it is not a limit by definition. So, you cannot say that the sequence can get arbitrarily close to plus infinity, because that's not true. Plus infinity is not a real number, by the way. Okay? But people say this, so that people say that the limit converges to infinity, which is nonsense, because if it converges to infinity, this is something that it cannot do by definition. But again, it can also be that if it's not. So in this case, you can say that if the limit is not finite, then it's divergent, by the way. Okay? So either plus or minus infinity, which could be the case. Now, if the limit is 0, then it's called a null sequence. That is, these are important ones. But again, these are the definitions, okay? So, I mean, this is just, you know, take that with a grain of salt, because it's a contradiction in itself. If the limit is plus infinity, let's say, then it's not a limit, by the way, okay? So, anyways, all right, so that's just something which I want to trash here, although it's expressed like that. Now, regarding convergent sequences, and basically I'm going to look at that. So let's say there is a sequence which is convergent. It's converging to the limit a as the sequence progresses. So if I say as the sequence progresses, this means that the index of that sequence tends to infinity. And let's say there is also another one which is also convergent to maybe to another limit without loss of generality. Now, what you need to know is that limits are additive. So this means that the limit of a sum of two sequences is going to be the sum of their limits, point blank, period, as the sequence progresses. So if the sequence A converges and the sequence B converges, then the sum is going to be also convergent, and the sum is going to, the limit of the sum is going to be the sum of their limits. Yes, as the sequence progresses, of course, right? I was interrupting it. So limits are additive. Limits are multiplicative. This means that the limit of their products is also going to converge to the product of the limits. Accordingly, I mean also, and it's not also, but accordingly. Does that make sense? Okay, so limits are multiplicative. So it's one converging to 2 and the other is converging to 4. Then the product will converge to 8. This is true without loss of generality. And that is also true if you perform divisions. Now the limit of a ratio is going to be the ratio of the limits, provided that the denominator is not going to be 0, but other than that, so at least B is not supposed to be a null sequence, but if it's not, then basically that is also true. Okay, so these are properties that limits have, especially I'm going to refer to that. And that is also true for limits of other kinds, of other sorts, probably. For example, convergence in probability. Okay, so where random variables are going to be involved, but that's something which I'm not going to do today. I'm going to do that probably, no, not next week, but in 2 weeks, because next week we skip the lecture. So we have 2 days on, 2 weeks on, 1 week off. Anyway, the Cauchy sequence will not be relevant for the exam, but a Cauchy sequence, just wanted to mention this. A Cauchy sequence is a sequence where members are getting arbitrarily close to each other. So as the sequence progresses, members are getting arbitrarily close to each other. Okay, so as both and m basically tend to infinity, okay, and that is basically true. So both are, I forgot to denote this, I'm going to correct that. So n and m will tend to infinity, by the way. And this is basically what is happening. So this means that the members are getting arbitrarily close to each other. Simple as, okay? I'm not going to waste your time based on that. Again, Cauchy sequence will not be relevant for the exam. So I'm not going to discuss the issue whether a sequence is a Cauchy sequence or not. Okay, you probably heard of that. Okay, but the issue is just because they're getting arbitrarily close to each other, it doesn't necessarily mean that they have a limit. So they don't even need to be basically having limits, or they don't need to be convergent, by the way. So if they're, the other way is true. So if the sequence is convergent, if they're getting arbitrarily close to the limit, then the members are also getting arbitrarily close to each other. That's something which can be shown. But just because they're getting arbitrarily close to each other, it doesn't necessarily mean that they are convergent. Okay, so that's not a one-to-one relationship, by the way. Anyways, okay, so I'm going to basically show you that one. So let's say, for example, I'm going to consider a sequence based on the set of rational numbers, so 1 plus 1 by n to the power of n. As the sequence progresses, all members are rational. Of course, it can be expressed by the ratio of 2 integers in this case. And the issue is that it has no limit in the set of rational numbers. It's not going to be convergent, okay? Although basically all members are rational, the sequence is not convergent, at least not in the set of rational numbers, because you might be familiar with that expression, 1 plus 1 by n to the power of n, as n tends to infinity is going to be, by definition, the Euler's number. Okay, so you've probably seen that. And that's not going to be a rational number, by the way, so it can be shown that it's not going to be rational. So there is a limit, but not on the set of rational numbers. So if I basically define that to be a sequence on a set of rational numbers, but as you see, a sequence defined on a sequence based on rational numbers does not need to have a limit. Okay? Because again, if there is a limit of that sequence on a set of rational numbers, that must be a rational number too. You understand? But it's not. Okay? You would need to extend it, by the way. But again, you will still have that the members are rational. So the sequence of rational numbers is not necessarily convergent, even if it's a Cauchy sequence, even if basically the members are getting arbitrarily close to each other. And that's something you can show, by the way. Okay, so the set is called complete if every Cauchy sequence has a limit in that set, but in case you can sense this is not true for the set of rational numbers, the set of rational numbers is not going to be complete. Whereas, for example, and that can be shown, you would need to define it, basically, and the set of real numbers is defined based on Cauchy sequences, by the way. So that make it to be a little bit more sophisticated, but I'm not going to. So I'm not going to define what real numbers are in this course. Anyways, okay, so again, just because sequences are getting, or members of sequences are getting arbitrarily close to each other, it doesn't necessarily mean that the sequence converges. Although if it converges, then this is going to be true. Okay? So if it converges, that's going to be the issue. I wanted to be quick because, again, this is not that important, but regarding convergence for functions, which is going to be important, similar or kind of definitions exist which resemble to that of Cauchy sequences. And we're going to discuss those too. So when it comes to limits of functions, you always have an underlying sequence which converges. So let's assume that basically xn is a sequence in the following, so hereafter, and that is also going to be true for every definition that you're about to see. Let's say you have a convergence sequence, okay, on a specific set, and that sequence has the limit p. Okay, so xn is a sequence, and the limit of that sequence is supposedly be p. And I'm going to address basically what limits of functions are. Now, the function is set to converge to, okay? And specifically, let's say it's set to have a limit 2 if the image is also convergent. So if you take the members of the sequence and put them into the function, by the way, you're going to get the images. And if the images converge too, then the function is set to be convergent. Okay? And the limit is supposedly be L. So capital L is supposed to be the limit. Now, it is not necessarily the case, and I'm going to show you examples based on that, that actually the limit of the images is equal to the image of the limit. It can be the case, okay? So it can be the case, again, so what you see here, this expression is the image of the limit, but it's not necessary. So it can be the case, but it's not necessary, okay? So the two can coincide, but they don't do it in general. Later you're going to see some examples, okay? So the image of the limit of the images is not necessarily going to be the image of the limit that the sequence X has, okay? You need to keep that in mind. All it is required for the limit of the function is that it is finite. That's the only thing that is required to be. Because if the limit is finite, then it's convergent by definition. So the images converge. Okay? Now, for most functions, that it is true. However, there are functions for which this is not true, that the image, or the limit of the image, sorry, is equal to the image of their limit. Okay? But that's something which I want to stress here. So, of course, as a sequence progresses. And again, this is also mentioned here. So you need to understand that the limit of the images is not necessarily equal to the image of the limit of the underlying sequence from which this is constructed from. But let's say most functions which you were familiar with, it could be the case. So it's actually true for the logarithm, for example. But again, I'm not going to base on that. Okay, so you could bypass the limit operator by the logarithm. So the limit of a logarithm is going to be the logarithm of the limit, by the way. So that's basically the issue of what it says. In this case, it would be because the logarithm is going to be a continuous function. But again, this is not necessarily the case here. Now, there is also the so-called left-handed and right-handed limit. I'm going to start by the so-called right-handed limit here. So this means that, let's say, the members are all greater than the limits of the sequence. Then this means that you're coming from the right. Okay? Now, the right-handed and the left-handed limits can be different. But if you're coming from the right, which means that the members are all greater than P. So it could be the sequence for that. You can also basically come from the left anyway. Okay, so then you say that if the images converge, then that is going to be the right-handed limit of that function. Okay, because it can be also, the limit can also depend on whether you're coming from the left or from the right when it comes to limit of functions. Okay, you're going to see examples later than that, so where I was explicitly calculating the left and the right-handed limit of functions. Okay, and then you might see that this is not going to be equal to the image of their limits. But again, this is just another story. Now, since there is actually the right-handed limit, there is also the left-handed limit, so this means that if you consider the left-handed limit, you're coming from the left. So the members are all, without any exceptions, okay, all of them are strictly less than the limit. If this is true, the limit of a function can be different, okay? There can be the case where both the left and the right-handed limits are equal, but it's not necessary, okay? So for example, okay, you're going to see that later on, so I'm going to collect those definitions first. Okay, so there is also the left-handed limit if you're coming from the left, and there is also the right-handed limit if you're coming from the right. Okay, so the question is not just basically what the limit of the images is, but the question is also, and that can also depend, the answer can also depend on where are you coming from. Okay, so I'm going to complete that definition. So in this case, I'm going to denote the left-handed limit of the function by L minus, okay, if there is, and the right-handed limit by L plus to distinguish between the two. And if they are equal, which can also be true, then I simply just refer to it as a limit, because if they're equal, it doesn't really matter where are you coming from, okay? Whether you come from the left or you come from the right, it don't really matter in this case. It can be different, but it's not necessarily the case. Okay? Yes?
What if you jump from left to like more?
Oh, you alternate, then it's not going to be convergent in that regard. If they're, I mean, then if they converge if they're basically they're equal, but they don't converge if they're not. Okay, that is going to be an issue, for example, for non-continuous functions in that regard, where the left and the right-handed limits of functions can be different. Okay, you're going to see what happens then. But again, if this is the case, then the images do not converge. Okay, they might be converging if you come from the left strictly, or you come from the right, but not in general. Okay, so that's the answer. It might be sequence of the images might be divergent. Okay, now again, in general, this is if they're equal, this is basically, it doesn't matter where you're coming from, by the way. Okay? All right, the only necessity is actually that the limits, or the limits, if there's, again, the issue whether you come from the left or from the right, is an issue, by the way, okay? But if it's not, all you need to have is just the finiteness of the of the limit of the images. Now, based on continuity of functions, this is going to be continuity, right? So if actually, and this is what it is, okay, the function is going to be called continuous. If, and that's the case, if the limit of the images, which you see here, is going to be the image of the limit. So if that is true, okay, so given that a sequence converges, and let me stress this, given that a sequence converges to a certain limit, okay, which is denoted by P, the images do the same thing, but not just that. They converge too, but not just that. So it's not just that the limit is going to be finite. The limit is going to be equal this time. Okay, so the limit of the images is going to be equal to the image of the limit this time. If this is the case, okay, then the function is called continuous. Okay, at that point at least. And if the function is going to be continuous at all points that it has on its domain, then itself is going to be continuous. So a function is going to be actually continuous if it's continuous at every point of its domain. I'm not sure if you understand this. So if this is the case, that the limit of the images is going to be equal to the image of the limit, whether you come from the left or from the right, it's not supposed to be an issue in case of continuity. All right? So keep in mind that continuity of functions is a local property. It can only be addressed at a given point. Okay? Whereas continuity on the whole domain, you would need to examine basically continuity of every single point that the function has. Okay? Usually it's associated with the fact that the function does not have any jumps. But keep in mind, it could be the issue because the function 1 by x, okay, which is looking like this, is still continuous because 0, where the possible jumps could occur, is not part of the domain of the function. Okay, so 1 by x is continuous. Okay? So again, non-continuous functions are associated with functions that have jumps. That is only partly true, okay, depending on whether basically, again, 0 is not part of the domain of the function. So again, and you only have to have continuity on the domain of the function, but not outside of it. You understand the point? That's the issue. All right, guys. Anyway, so that's not going to be that important. There is also right continuity and its left continuity. So if you come from the left, it could be the case that the limit of the images is going to be equal to the image of the limit. And if you come from the right, it could be also an issue. Okay? So if you come from the right, and then you have that the limit of the images is going to be equal to the image of the limit, but only if you come from the right, not if you come from the left. Then the function is going to be called right continuous. And if this is true, basically if you come from the left, because again, in this case, check this out, the members are greater than the limit, so then you come from the right. And if the members are less than the limit, and that is true, then you have basically you're coming from the left. Okay, so this is also going to be addressed here. Check again, this is the issue. Okay, if the members are less than the limit, and that could be the case that, for example, the image of the limit, the limit of the images is equal to the image of the limit. But only if you come from the left, then the function is at least left continuous in that regard. So that could be the case, right? But that is just basically it. So there is left continuity, right continuity, and if the function is left and right continuous, right, then it's going to be continuous. Of course, a real valued function of real numbers. Okay, so if you only come either from the left or from the right, okay, because if there is multiple dimensions, you know, it doesn't make that much sense if you say come from the left or come to the right. Anyway, okay. Okay, so when it comes to limit of functions, it's also going to be, could be important where are you coming from regarding the sequence. That is actually the underlying sequence here. Okay? Does that make sense? I'm not sure if you understand this properly, but again, I'm going to basically just discuss this when it comes to examples, so you might understand this better. Okay, now there is also the issue of Càdlàg functions. This is a specific type of functions. Is anyone speaking French here? Okay, nobody? Nobody speaks French? Lil? Okay, maybe you can help. I have, but it's a long time, so it's over 40 years now. Basically, the Càdlàg is a French term. It's an acronym. I'm going to show what it is. So it's a function that is, again, has two things. It must be right continuous. That's number one. So when you come from the right, or if you come from the right, for every point of the domain, the limit of the images of the function is going to be equal to the image of the limits. That is always true, but only if you come from the right, not necessarily from the left. Okay, so that is true, but only if you come from the right. Okay, so because it is right continuous. You understand what I'm saying? But if you come from the left, at least you have finite left-handed limits. So that's not necessarily true that the limit of the images is equal to the image of the limit. Okay, it could be. So any function that is continuous is automatically a Càdlàg function because it is right continuous and it has finite left-handed limits. That is always true. Okay, but it could be that when you come from the left, so as you come from the left, it can happen that the images do not converge to the image of the limit. But at least those images do converge. Okay, so at least they do, but not necessarily to the limit of the images. You're going to see some examples, but for example, just if you're not sure about that, the cumulative distribution function of a continuous random variable is going to be a typical Càdlàg function. Okay, later I'm going to show you some. So, well, you have the stair function, right? Typically, when it comes to random variables, that is going to be a Càdlàg function. Now, Càdlàg is an acronym. Again, I don't speak French, so unfortunately, so again, it comes from continuer à droite. So à droite means from the right. I know that, but that's it. So continues from the right, okay? And it has finite, à gauche means from the left, so with finite left-handed limits, okay? So it's right continuous with finite left-handed limits, okay? It can also be left continuous. If it's right and left continuous, is also a Càdlàg function, right? But if it's a Càdlàg function, it's not necessarily going to be left continuous, but it must be right continuous. You could also reverse it, but that is something which I'm going to discuss sometimes, okay? We're going to have stochastic processes, maybe, that are going to be Càdlàg functions, okay? Because they have jumps or things of a kind. And anyway, okay, where the paths are going to be actually right continuous, almost surely, okay, or almost everywhere, but actually with finite left-handed limits. I'm not sure if you understand that, but I'm going to basically just, again, so if you haven't seen a cumulative distribution function of a discrete random variable, typically it's going to be a stair function, so it's going to look like this. more or less. So here's a hole, and then it continues over here, and then, you know, things of that nature. This is a typical Càdlàg function. I'm going to discuss that in detail. Okay? All right? So cumulative distribution functions are Càdlàg functions, all of them, basically. Right continuous with finite left-handed limits. No exceptions. All right? Okay. Again, now, based on that, I'm going to also address uniform continuity. Now, that is a global property. So continuity was a local one at a given point. And uniform continuity is a global one. So let's say you got two sequences, and where the two sequences are going to get arbitrarily close to each other. Now, if the sequences are getting arbitrarily close to each other, okay, as they progress, kind of like a Cauchy sequence, by the way. So if you look at that as a joint perspective, okay, then the images must do the same thing. Okay, so let me stress this. So again, this is basically what the issue is. If those two sequences are getting arbitrarily close to each other, which means that their distance converges to zero as those sequences progress. You understand? So getting arbitrarily close to each other. The images must do the same thing. If they do, then the function is going to be uniformly continuous. And if they don't, then it's not. Okay, so that's a global property, by the way. Okay, which means that that's not local because I'm not addressing single points. Okay, so whenever two sequences are getting arbitrarily close to each other, the images of those sequences must do the same thing. If they don't, then basically you don't have uniform continuity, which is a stronger property, by the way. So any function that is uniformly continuous is also going to be continuous, by the way. So if images of two sequences are getting arbitrarily close to each other, then, if the sequences are getting arbitrarily close to each other, then the images must do the same thing. Okay? That's basically what uniform continuity is. I will, again, take examples based on that. And then you have absolute continuity, which is a little bit more difficult. So regarding absolute continuity, which is a very, very strong requirement, by the way, so it's just very, very few functions which are not absolutely continuous, you're going to have the following thing. So you're going to have a sequence of open intervals. So instead of basically, having two different sequences, you're going to create a sequence of open intervals. And all of those open intervals are pairwise disjoint. That is also a requirement, which is relatively difficult to achieve, but it can be done. So it's very technical. Okay? So let's say you have a sequence of open intervals, which, for all of them are going to be pairwise disjoint. Okay? And the issue is this, and okay, all of them are going to be on an interval with finite endpoints. So all of them, okay, are coming from an interval, are subsets of an interval where the interval capital I has finite endpoints. So that is actually a compact interval more or less, or a compact set of real numbers if you think about that. Now a function is said to be absolutely continuous if the total sum of the distances of the images are converging to zero, if actually the total sum of the distances, or the length of the interval, because if you calculate the distance of the upper and the lower endpoint, you find that this is actually the length function of those intervals. So if the total length is converging to zero, then the images must do the same thing. So this means that actually the function is squeezed in, more or less. Okay, because if the total length, this is the total length of the interval, so if you take the sum of all of them, and that converges to zero, then the images must do the same thing. It's very difficult to imagine what it would be like, and it's also very difficult to, relatively speaking, to construct even a function that is not absolutely continuous. But if you want to Google it, for example, you can Google the Cantor function or the Cantor distribution if you like. The Cantor distribution is a probability distribution where the cumulative distribution function is not absolutely continuous, but it is continuous. Okay, so But that's very, relatively speaking, relatively difficult to understand. So if you're not sure what it is, okay, what its definition would be, then it doesn't really matter. Okay, so I want it to be as accurate as I can in order to define those things properly. Anyway, okay, so those are the definitions. Okay, so the sum of the distances of the images of pairwise adjoint intervals. So blah blah blah. So A of B of C of D of D. Okay, so nobody knows, but basically what it means that anyway. So that is a sum of the distances, or the sum of the length of the images of pairwise adjoint open intervals. Pairwise adjoint open intervals can get arbitrarily small if actually the total sum of the length of these intervals is getting arbitrarily small. Okay, so that means that somehow, you know, the function is squeezed in. It's very difficult to understand this, I have to admit, but it's not going to be that important for the exam. So if you want to skip it, I'm fine. Okay, it's not that big of a deal. It is big of a deal, but it's very difficult to deal with that. Now, okay, the following chain of implications is to be considered, by the way. So if a function is absolute continuous, which again, most functions are, so it's very, very difficult to construct a function which is not. The Cantor distribution would be an example where the distribution is not absolutely continuous. I took it out because I don't want to waste your time. But it's a very, very strong requirement on a function. If a function is absolutely continuous, then it's going to be uniformly continuous. And if it's uniformly continuous, then it's also going to be continuous. Okay? And if it's continuous, then it's left and right continuous, by the way. So if you want to go further, you can. Okay, but that is a chain of implications that is actually necessary. Now, why I'm introducing absolute continuity, although I'm not looking at into the detail, because if a cumulative distribution function is absolutely continuous, then the density function exists. That is a sufficient condition for the existence of the density function. And it's very difficult to make sure that the density function of a random variable would exist without absolute continuity of the distribution function. So when you Google that, when you check that out, the Cantor distribution, which is very abstract, by the way, so it's very, very difficult to understand it, but relatively speaking, but it has no practical relevance on the other hand, so I don't want to dive into that far, okay? Within a PhD course, maybe I would, but I don't want to waste your time, so I like to basically to consider theoretical things, but I understand that you want to do more applications, so I will basically have to stop somewhere, okay? But a Cantor distribution is going to be a distribution with a continuous cumulative distribution function without a density. And you maybe learn in undergraduate courses that if the cumulative distribution function of a random variable is continuous, then the random variable is going to be continuous as well, which is not true. Okay, so it was a lie. I mean, I did it myself, so okay, I don't want to say I can sleep at night, but anyway, so it was a lie. Okay, so if you thought of that is the case, that it was a lie. If the cumulative distribution function is absolutely continuous, then the function will have a density and not. So continuity is not enough for the density function to exist, by the way. Okay, so that's a point. But anyway, okay, let's take examples finally. So then you see basically what it is. I'm going to use or consider limits of functions, and then of course after that continuity. So I'm going to look at the function where it's either equal to 1. Now it is equal to 1 if the argument is equal to 0, and it's going to be equal to 0 if it is not 0. So the function, again, you might not know how it looks like. So that's the x-axis. Here this is the y-axis. You have a point 0, and then on the y-axis you have the point 1. And there is a single dot here. So if you put in 0, right, you should see it. If you put in 0 into the function, you're going to get 1 out. So 1 is going to be the image of 0, as you see, right? And for all other actually points, you're going to have 0 coming out. So this is basically how the function looks. Okay, you see? All right. Now, although I want to show you that basically this is an interesting example, because although the left and the right-handed limits of the functions are equal, the function is not going to be continuous. So for the left and for the right right-handed limits to be equal, this is not going to be sufficient for continuity of the function. It is necessary, but it's not sufficient, by the way. And that, therefore, I decided to look at that. Now, I want to address the right-handed limit of the function first, okay, because that is basically what you might not be familiar with. So this means that at point 0, of course, because that's the only point of interest here, okay? So this means that you're coming from the right. So whenever you are maybe here and you tend to 0, right? Okay? And let's say the sequence does that. So you create a sequence that converges to 0 from the right, okay? Which can be done. It's not difficult to do. It must be true for every sequence there is. And the question is, to which point does the function converge? Do the images converge to? Now, what happens to the images? Now, whatever you put into the function, you're always going to get 0, right? So this means that the right-handed limit of the function is going to be 0. Even if you come from the right, it doesn't really matter. So 0 is going to be the right-handed limit of the function, even at that point. You understand it? Okay? So because whatever you put into the function, if you come from the right, you're always going to get 0 out. Okay? So the right-handed limit of the function is going to be 0, by the way. Okay? Now 0 is finite. Everybody knows this. Okay? So that the function has a right-handed limit. Okay? At that point. That is still true. You understand this? Now, again, so the function has a finite right-handed limit, and it is not just basically at this point, but every other point there is. Okay? So the function basically will have finite right-handed limits at every point of its domain. Okay? Now there is no name for that function, but okay, it has finite right-handed limits at every point of its domain. I don't know how to call them, okay? But it's always going to be true. Again, so the only point of which could be critical is actually the point 0. Okay? But every other point is quite clear. Okay? So if 0 does that, so does every other point. All right? Okay, and that is also true if you come from the left, by the way. So when I look at basically the left-handed limit, which I'm also going to look at, so when you come from the left, this means that the sequence here that you're generating is converging to 0, but from the left. So you're here. Maybe you start from here, and then you converge to 0. And the question is, what happens to the images? And the answer is not much, because whatever you do, okay, if you're here, all that you would get is 0. So the images will be actually converged to 0 as well on this side. So as you see, basically the left-handed limit and the right-handed limit of the function at point 0 is equal. But the function is still not going to be continuous. Okay, so that is not actually sufficient for that. Okay, but that's basically function that would be. So the function has finite left-handed limits at every point of its domain. Okay, all right. So when you would examine whether the function is a Càdlàg function, at least you always have finite left-handed limits. But you don't have right continuity. I'm going to show you that one. So it's not going to be a Càdlàg function, by the way, because it's not going to be right continuous, but it will have finite left-handed limits. Okay? You understand the point? Now, regarding continuity, which I'm also going to examine, I'm going to split that into two parts. I'm going to check whether the function is right continuous and whether the function is left continuous. The only critical point is going to be the point 0, because for every other point the function is right continuous. Whatever you put into the function, you're always going to get 0 coming out, except at that point 0. You understand it? So that is only the crucial point. But one point is enough to blow it off. Okay? So if I look at basically the right-handed limit of the function again, which I already did, so I don't want to do it again, but if you want to examine that, you find, and that's going to be crucial, that the right-handed limit of the function is not equal to the image of the limit of the sequence that is coming from the right. Because the image of 0, which is the limit actually, all right, of the sequence that is underlying here, the image of that is going to be equal to 1, and that's something else. So this means that the images of that sequence do not converge to the image of the limit. You understand? They converge, but not to the image of the limit. So that's finite. You see? So the right-handed limit is finite. So this means that they converge, but not to to the image of the limit. So this means that the function is not right continuous at that point. Now, if the function is not right continuous at any point, then the function cannot be right continuous at all. You understand? So one point is enough to blow it off, even if it's right continuous at every other point there is. You understand what I'm saying? I mean, there is a jump here, right? So the function jumps here to basically to that point, right? So you take it out, right? It cannot be continuous, but I wanted to show you why. Because it's not right continuous. Now, if it's not right continuous, it cannot be continuous either, right? So that is also true. So regarding continuity, that's basically blown up. And it's not going to be left continuous also, okay? So the function is not right continuous at that point because the images of the sequence do not converge to actually to the image of the limit. The image of that point. You see? That's the point. That's the issue. You see? All right? If they did, then it would be also right continuous. But they don't. You understand the point? So that's also the way to look at that. And if you come from the right? And it is also true if you come from the left. There is no difference. If you come from the left, that is also going to be true. So I just wanted to basically mention that one. If you come from the left, you see it over here. So you have a sequence that converges to 0, but from the left. And you look at the left-handed limit of the function at point 0, which I already did, which is finite. Okay, that is still true. It is finite, but, again, but, it's not equal, and this is what you see, it's not equal to the image of the limit, to which basically the underlying sequence converges to. So the function is neither left nor right continuous at that point. But anyway, if it's not left continuous at any point, it cannot be left continuous at all, and that is also true for right continuity, and that is also true for continuity, by the way, itself. So when it comes to real valued function or real numbers, if it is left and right continuous, then it's going to be continuous. Okay, but it's not. So continuity is actually over. You understand? If it's continuous, if a real valued function or real numbers is continuous, then it's going to be left and right continuous. And if it's left and right continuous, then it's also going to be continuous, but only for that class most of the time, which is actually the most common case. But again, this is basically what it is. You understand the concept now? Okay, so again, this function has finite left and right-handed limits, but it is neither left nor right continuous because those limits are not equal to the respective image. The limit which shall come out here are not equal to the respective image of the limit of the underlying sequence, which must be the case if the function is supposed to be continuous. All right. Okay. I don't know what people are looking at. Why don't you go out? Okay, it's almost 7 p.m. All right. Now, okay, let's go back, and I was already establishing the issue that the function has finite right-handed limits. Okay, but although the function is not right continuous, right, which was the case, so it's not right continuous, it is, and check this out, it is, and that is important, right continuous. Now, it's not right continuous, but it is right continuous, check it out, almost everywhere. Because the length of the set, and this is basically the issue, right? Almost everywhere, except 0, right? You see? Because if you put 0 into a set, this is going to be a countable set. And the length of any countable set, as we mentioned before, is 0. You understand the point? Right? So the image of that is going to be, let's say, is 0, right? Okay? So that is 0 because the set is countable. And except that, so the complement of that, this is not going to be true, so this means that is going to be right continuous almost everywhere. And the set of all points at which the function is not right continuous has length 0. Okay, if you use a length function. So it's not right continuous, but it's right continuous almost everywhere. Okay, well, here you have a property, okay? So if you find that basically the property is not true for countable many elements of a function, then, and for every other there is, then you can also argue that is right continuous almost everywhere. That's a term which I'm going to use frequently, okay? Or left continuous almost everywhere, or continuous almost everywhere. It's also going to be continuous almost everywhere because it's right continuous almost everywhere and left continuous almost everywhere. You understand it now? Okay? So that's a quite interesting term, by the way. And that is also the case when it comes to left continuity. So it's not left continuous, but it's left continuous almost everywhere. Why it's not left continuous? Because, again, I mentioned before, the limit of the images is not going to be equal to the image of the limit. All right? Now let's do another one, if you allow me to do it. Okay? We're going to look at the so-called uniform continuity, which I want to address here. So as I mentioned before, 1 by x is a continuous function. This is how it looks, at least in this part. Okay, if you basically complete that, this is how it would be. But I'm only focusing on, let's say, non-negative elements. And I'm going to basically define two sequences. The first one is going to be the sequence 1 by n, where n is basically the index of the member. So the first member is going to be 1, the second is 1/2, the third is 1/3, and so on. And I'm going to create another sequence which is basically twice as large as the first one. Okay? So the first member is 2, the second is 1, the third is 2/3, the fourth is blah, 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 and so on. Okay? Now, the question is, what does the difference of the members do? And as you see, basically, you could do, I didn't do it, but this is something which you would need to calculate. So 1 by n minus 2 by n, of course, right? This is basically what you would do. Is going to be negative 1 by n, and negative 1 by n is converging to 0 as well. Okay? So you see, the members are getting arbitrarily close to each other as the sequence progresses. They're both convergent, by the way, but that's not even necessary. Okay? What's necessary is actually, and this is basically it, is that the members are getting arbitrarily close to each other as both progress. Now, the question is, again, the question is here, if you want to establish uniform continuity, the images must do the same thing. And you'll find that they don't. Okay, so when it comes to the images of those, okay, what is the image? Actually, the image is a reciprocal of the member. So you would just simply take basically the inverse. And what's the inverse of 1 by n? That is going to be n, of course. Okay, so that's a reciprocal of n. And the reciprocal of 2 by n is going to be actually n by 2, by the way. And if you subtract the 2, this is going to be 1/2 times n. And 1/2 times n does not converge to 0 as n progresses, or as the sequence progresses. You understand the point? So if basically sequences are getting arbitrarily close to each other, the images do not. Again, not necessarily, but they have to. So, and that's basically what the point is. Okay, so this thing will not converge, okay, to 0. And for uniform continuity, they would have to. Okay, so as both progress, this is not going to be the case. And one example is just enough to blow it off. All right? Now, as I mentioned before, the function is continuous, okay, because it's left and right continuous on its domain. That is true. 0 is not part of it, so you don't need to examine that, what is happening there. But it's not uniformly continuous. And if it's not uniformly continuous, then it cannot also be absolutely continuous, by the way. But that's just another story. Okay? Because for absolute continuity, you could not squeeze that in. Okay? So the total length of this image, basically of the sequence of open pairwise disjoint intervals, will not converge when it comes to the images. Anyway, is that understandable now? Okay, so that is also going to be true. Now, if you allow me to take 5 minutes, okay, because I was late, so I want to finish that lecture. It's not going to be long. I'm going to summarize basically properties of cumulative distributions functions that they have. Okay, so again, what is a cumulative distribution function? The cumulative distribution function at point small x will give you the probability that a random variable is not greater than that. Okay, so whatever you put into the function, this is basically what it would be. Okay, I think you've seen this before. The first thing that I want to mention is that it's non-decreasing. Okay, so again, if x increases, then the probability at least is non-decreasing at all. Okay, because if x increases, then basically 1 Borel set would be actually always a subset of the other. And if one is a subset of the other, then the probability of the subset cannot be greater than the probability of the superset. We already mentioned that before, so that's the reason why it's non-decreasing, by the way. Now, what it's also going to do is going to be it's right continuous. Always, all the time, actually, but with left-handed limits, which are finite. So it's a Càdlàg function, by the way. So any cumulative distribution function is going to be a Càdlàg function. Even if it's continuous, it's also going to be a Càdlàg function. All right? Now, in addition, it is continuous almost everywhere. So a step function where basically the number of steps is countable is still going to be continuous almost everywhere, even if it's not continuous on a countable set. Okay, almost everywhere means, as you mentioned before, right? As we mentioned before, the set for which is not true has zero length, and if it's countable, which is going to be the case, then if it's discrete, and that's where the jumps are, if they happen, the set of visualizations is going to be countable, and that's the point. Okay, so it's not going to be continuous, but it's going to be continuous almost everywhere at least. And the probability that x is greater than a, for example, but not greater than b, is going to be obtained by the difference of the cumulative distribution function at point b minus the cumulative distribution function at point a. That is always true. Whether x is discrete or not, it doesn't really matter. Okay? Now, these are basic properties that every cumulative distribution function has. Whether the random variable is discrete or not, it doesn't really matter. Now, when it comes to basically further cases, so you want to get the probability that x is strictly less than b, for example, not greater than that, but b. Okay, so this is not the cumulative distribution function at point b in general, but it's going to be its left-handed limit, which is going to be finite. So that's why basically the Càdlàg property comes here. This is whatever it is going to be finite. That must be the case. All right? Because it's going to be finite, right? But it is not necessarily equal to the image of the limit, because the function might not be continuous at that point. Okay? So if there is a jump, right? For example, when the random variable is discrete at that point, all right? Okay, so it's a realization. This is not what it's going to be. Okay, so that's not necessarily actually the limit, the image of the limit, right? And the image of the limit would be the image of b, because b would be the limit. You understand the point, right? Does that make sense now? Okay, so it's left continuous. Right continuous, but with existing left-handed limits. Okay, so that's a left-handed limit, which is finite. I forgot to mention that, but it's basically clear. All right, so if left-handed limits are finite, then it would be. Now, this allows me to address basically what the probability of x being equal to b is, because this is actually the probability that x is not greater than b minus the probability that x is less than b. Okay? That is also clear. Now, if these two are equal, then the probability of that is going to be 0. Which is the case if the function is continuous at that point. Because if the function is continuous at that point, then the left-handed limit at that point is going to be equal to the image of the limit, which is going to be the image of b after all. Okay, so it's not going to be 0 in general, but if the function is continuous at that point, it is. Okay, so if it's continuous at that point, then it's going to be equal to 0. And that clearly follows from this property, by the way. So if there is no jump, then basically the probability at that point is going to be 0, by the way. And the limit of it, if basically x tends to minus infinity, is going to be 0 all the time. All the time, whereas basically the limit of it, if x or the argument is increased, okay, beyond any limits, is going to be equal to 1. All right, so these are properties that all cumulative distribution functions have. Whether the random variable is continuous or discrete, it doesn't really matter, or neither. Okay, so that's the third type, but it's not going to be relevant. Now let me address it. So basically the existence of probability mass functions, which I mentioned before. So I'm going to be very quick, and then we're done. If the cumulative distribution function of the random variable is absolutely continuous, that is efficiency. I'm not sure whether it's a necessity, but probably not. Okay, could be very difficult to weaken that. issue. If it is absolutely continuous, which I mentioned before what it is, that was a technical issue. So absolute continuity means that the total sum of the length of the images from the pairwisely disjoint open intervals, okay, is going to converge to 0 if their total length do, okay, that is absolute continuity. Then there is another function which we call the density function, satisfying the following thing. So the cumulative distribution function at point x is going to be the integral of that function from minus infinity to that point. Okay, and the function which satisfies that, where the integrator is going to be different than basically the argument of the cumulative distribution function, is going to be the density function, is called the density function of the random variable. So PDF, okay, PDF is not what you thought of would be. PDF is the probability density function of the random variable then. And that exists if, among others, the cumulative distribution function of a random variable is absolutely continuous. And then second, the random variable is said to be continuous then. So that is a continuous random variable. Okay, so random variable is called continuous if it has a density, okay? And sufficient for that is going to be that the cumulative distribution function of it is absolutely continuous. Now, sometimes we say the random variable is absolutely continuous, but I dropped the word absolute, so I'm just going to refer to that as to be continuous. Okay? All right, guys, so these are things that you've probably seen here and there, but I wanted to summarize that to be basically more, to present them in a structured way. It's very technical. It's true. We haven't talked about stochastic processes yet, but we will. Okay, so we're going to basically talk about that. Now, next week there is not going to be a lecture, so we take 1 week off. In 2 weeks, I'm going to prepare everything, so if something is ready, I'm going to post it, so you'll be informed that you can download these things. Are you in the group, all of you? Okay, so in the new group which I created. Okay, so if you're not, basically, please bypass the link. And I'm going to keep you posted, and I'm going to see you in 2 weeks. Until then, goodbye.